There's a moment most of us have had. You're standing in your kitchen. You ask your smart speaker something simple, something any 8-year-old could answer. And it either gets it completely wrong, gives you something unrelated, or just, unhelpfully, says it doesn't know. You've probably wanted to throw it against the wall. And if that's your main experience of artificial intelligence, a device that sometimes works and sometimes doesn't, that can play your music but can't hold a conversation, that was sold to you as the future and occasionally feels like a very expensive timer, you might reasonably wonder what all the fuss is about. Here's the thing. That smart speaker is AI, but it's the smallest, oldest, most limited version of the idea. Judging AI by a smart speaker is like judging the internet by a 1994 dial-up connection. What we're really talking about, what this course is about, sits somewhere entirely different on a spectrum that researchers have been arguing about for decades. At one end, artificial narrow intelligence, ANI, the smart speaker, the spam filter, the recommendation algorithm that knows you want to watch that show. These systems do one thing, sometimes extraordinarily well, but take them outside their lane and they collapse completely. At the other end, artificial superintelligence, ASI, a hypothetical system exceeding human intelligence in every domain: science, creativity, reasoning, social judgment. Theoretical, doesn't exist, but not everyone thinks it will stay that way. Geoffrey Hinton, the man most responsible for making modern AI possible, resigned from Google in 2023 specifically to say publicly that he was scared. And then there is the middle. This is where it gets interesting. Because what has emerged in the last 5 years doesn't fit neatly into the narrow category anymore. It crosses domains. It handles problems it was never explicitly trained on. It reasons, weighs options, adapts to context. It can help you draft a contract, analyze a financial statement, and then explain its reasoning in the same conversation. Researchers call this artificial rational intelligence, ARI. The term comes from Russell and Norvig's Artificial Intelligence, A Modern Approach, the foundational AI textbook, which frames intelligence as the ability to act logically, perceive an environment, calculate options, and make decisions to maximize an outcome. ARI is not AGI. It doesn't have common sense. It can't learn continuously from experience. It can fail in ways that would baffle a 12-year-old, but it is not the same as a smart speaker. There is a second map worth knowing. 4 capability types, proposed by AI researcher Arend Hintze in 2016. Reactive machines. No memory, responds only to the present moment. Deep Blue, the chess computer that beat Kasparov in 1997, was a reactive machine. Limited memory, uses recent data to inform decisions. Self-driving cars, current AI assistants, most of what you interact with today. Theory of mind, a system that genuinely understands beliefs, emotions, and intentions. We are at the research edge of this. And self-aware, conscious, subjective experience. Theoretical, does not exist. Most of what we work with is type 2. Limited memory, ARI territory. And here is where it gets human. Because we have a tendency, documented since 1966 when a computer scientist at MIT named Joseph Weizenbaum built the first chatbot, we have a tendency to project more onto these systems than they actually have. Weizenbaum's chatbot, Eliza, did almost nothing. Pattern matching. It reflected your words back as questions. You said, "I feel sad." It said, "Why do you feel sad?" That was the entire mechanism. And yet his own secretary asked him to leave the room so she could speak to it privately. He spent the rest of his career writing about this. He called it the Eliza effect, the human tendency to attribute understanding, warmth, empathy, intelligence, to a machine that has none of those things. In 2023, 57 years after Eliza, 10 million people were using a companionship AI called Replica. When the company changed the software in February of that year, users described grief. Some reported suicidal ideation at the loss. The machine hadn't changed its capacity for understanding. It had never had any. What changed was the fluency of its responses, and that was enough. There's a version of this playing out in organizations right now. Someone trusts an AI output a little more than they should because it arrived fast, because it was well formatted, because it sounded confident. A professional who knows their domain catches what's wrong. Someone who doesn't might not. It's a bit like a new relationship. Do you trust who they actually are or who you want them to be? Knowing the difference, knowing what good looks like before you trust what confident looks like, is the prerequisite for everything that follows. This is where we are. ARI is real. AGI is not. The gap between them is where the risk conversation lives. And navigating that gap requires understanding not just what these systems can do, but how they actually work, which is where we go next. Before anything else, you need a map. Because what follows, the details of how machines learn, how they see, how they understand language, how they generate content, only makes sense if you know where each piece sits relative to everything else. Artificial intelligence is the outer boundary, the whole field. The attempt, as Afan Samad put it, to get computers to learn and act as humans do, and improve their learning over time in autonomous fashion by feeding them data and information in the form of observations and real-world interactions. That is the territory. Within AI, machine learning, a subset, the science of using statistical methods to enable machines to improve with experience, without being explicitly programmed for every situation. The key word is learning, not following rules. Learning from data. Within machine learning, deep learning, a further subset. It takes the ML approach and implements it through multi-layer neural networks, an architecture that makes certain problems suddenly tractable, problems that had defeated traditional ML for decades. And then, this is the part most people miss, natural language processing is a parallel field. It overlaps with deep learning. Where they overlap is where you find generative AI. Gen AI needs both, deep learning for the computation, NLP for the language. It sits at that intersection. Large language models, GPT-4, Claude, Gemini, are a specific type of generative AI. The IBM technology team use a useful term for them: foundation models. Massive systems, pre-trained on enormous datasets, general enough to be adapted to a wide range of tasks without being rebuilt from scratch. The model powering a legal drafting assistant and the model powering a medical records system might both be the same foundation model, fine-tuned differently. One more distinction worth getting right early. When people talk about the algorithm, they often mean the model. These are not the same thing. An algorithm, as Schmelzer and Walsh explain in the AI Today podcast, is a set of steps that describes how a computer should process data in order to obtain a desired result. For machine learning, the algorithm is the recipe. It tells the machine how to learn. The model is what you get when you apply that recipe to data. It is the computer's learned representation of the world. A model trained on medical scans for cancer detection knows what a tumor looks like. That knowledge lives in the model, not the algorithm. You use the model for inference. You use the algorithm to build the model. Algorithms are created rarely. When a new one appears, the whole field notices. Models get trained constantly. Every organization deploying AI is producing models. Now, the map is visible. Let's go into the territory. In March 2016, a Go player named Lee Sedol sat down to play a computer. Go is not chess. Chess has roughly 10 to the power of 120 possible game states. Go has 10 to the power of 170. The number of possible Go games is larger than the number of atoms in the observable universe. For decades, experts said computers would never beat the best human players. The game was too complex, too intuitive, too human. In Game 2, Move 37, AlphaGo placed a stone in a position that no human player would have chosen. Commentators initially thought it was a mistake. One expert said it looked like it came from a completely different era of Go. Lee Sedol left the room. He needed 15 minutes to compose himself. AlphaGo won 4 games to 1. What beat Lee Sedol wasn't programmed by a human who knew how to play Go well. It wasn't given rules. It wasn't shown the right answers. It learned. And the way it learned is the foundation of almost everything interesting happening in AI today. There are 3 core types of machine learning. Each works differently. Each has applications where it excels, and each has a failure mode worth understanding. Supervised learning is the most intuitive. You show the machine thousands of examples, each one labeled with the right answer. Photos of tumors labeled malignant or benign. Emails labeled spam or not spam. Medical scans labeled normal or abnormal. The machine learns the pattern. Then it applies that pattern to new data it has never seen. In 2018, DeepMind's AI, trained on 128,000 labeled retinal scans, detected diabetic eye disease at the level of a specialist ophthalmologist. The same year, Amazon shut down an AI hiring tool. It had been trained on 10 years of the company's own hiring data, mostly male hires. It learned to penalize CVs that included the word women's. It downgraded graduates from 2 all-women's colleges. The AI didn't have a bias. It learned from data that did. Supervised learning trains on human decisions. If those decisions were biased, the model becomes biased, at scale, with the authority of an algorithm. Unsupervised learning works without labels. No right answer. You feed the machine raw data, and it finds structure, clusters, patterns, anomalies that you didn't ask it to look for. It tells you what's there, not what you expected to find. Researchers at MD Anderson Cancer Center used unsupervised clustering of tumor gene expression data to reveal cancer subtypes that matched patient outcomes, subtypes no pathologist had previously defined. The pattern was in the data. No human had found it. Cambridge Analytica used the same approach on Facebook data, 87 million users, to infer personality types and target political messaging without consent. The pattern finding is neutral. What you do with the patterns is not. Reinforcement learning is how AlphaGo learned. Trial and error, reward and penalty. The system plays a move, receives feedback, did that lead to a win or a loss, and adjusts. Millions of iterations. The system doesn't learn rules, it learns to optimize for an outcome. Move 37 was a move that AlphaGo had calculated would win the game in the long run, even though it looked wrong in the short term. No human had taught it that. It emerged from the training process. Microsoft's Tay chatbot used the same principle. Launched on Twitter in March 2016, it was designed to learn from conversation. Coordinated users taught it racist and anti-Semitic content within 16 hours. Microsoft shut it down. Reinforcement learning optimizes for whatever the reward signal is. The reward function determines what the agent becomes. This is the principle underneath all 3 types. The machine learns what it is taught, through examples, through patterns, through feedback. If the examples are biased, it learns the bias. If the reward is wrong, it optimizes for the wrong thing. If the data is incomplete, the gaps become blind spots. The professor's slides illustrate this progression through one of the most studied examples in RL research, Pac-Man. A basic Q-learning agent on a small grid eventually learns, but needs 11,000 games to reach 77% accuracy on a medium grid. Add handcrafted features, approximate Q-learning, and performance jumps to 87% in just 50 training games. But those features require human expertise to define. What to look for, which signals matter. Switch to deep Q-learning, a neural network that extracts its own features from raw pixels, and the agent handles complexity no human could hand-engineer. Pac-Man isn't just a game. It's a compact demonstration of exactly why deep learning changed what was possible. Not faster Q-learning, but learning that doesn't require humans to tell it what to look for. There is a fourth approach worth knowing, one that has made the biggest models possible: self-supervised learning. Rather than labeling data by hand, the model generates its own training signal from raw text. Predict the next word, mask a word, and predict what it was. The label is already in the text. Train on the entire internet. That is how GPT-type models were built, not labeled by humans, self-labeled at a scale no human annotation project could match. In 2026, the best practice is combining these approaches with human feedback at key points, a process called RLHF, reinforcement learning from human feedback. The model learns from humans, but which human feedback counts is governed. Because we have seen what happens when it isn't, the lesson from all of it: how a machine learns shapes what it knows, what it misses, and what it gets wrong. You cannot evaluate AI output without understanding the learning process behind it, which leads to the question of what happens when machines learn to see. In 2006, a team of researchers set a challenge. They built a database of images, 1.2 million photographs, 1,000 categories, dogs, cars, chairs, aeroplanes, labeled by hand. They called it ImageNet, and every year they ran a competition. Teams from around the world submitted algorithms to see which could identify the images most accurately. The best human performance was around 5% error. For 5 years, the winning algorithms hovered around 25%. Progress was slow. In 2012, a team from the University of Toronto entered. Their error rate was 15.3%. The second-place team scored 26.2%. The team was led by Geoffrey Hinton, the same Geoffrey Hinton who would later resign from Google to warn about where AI was going. Their system was called AlexNet. It used a deep neural network, layers of mathematical functions loosely inspired by the structure of the human brain, each layer learning to detect increasingly complex features, edges, then shapes, then objects. It changed everything. Within 2 years, deep learning was the dominant approach in computer vision. Within 5 years, it was outperforming humans on standard benchmarks. What followed over the next decade is one of the most remarkable sequences in the history of technology. 2016. Tesla's autopilot system failed to distinguish a white truck against a bright sky. Joshua Brown, driving a Tesla on a Florida highway, died. The vehicle's camera-based system, trained on thousands of driving scenarios, had never learned to handle that specific combination of conditions. The machine learned what it was shown. It hadn't been shown everything. Real-world edge cases don't wait for training data to catch up. The same year, 2016, a different application of the same underlying technology was spreading through internet forums: deepfakes. GAN architecture, generative adversarial networks, originally designed to generate realistic images, repurposed to superimpose faces onto video without consent. The same deep learning, completely different intent. Let's pause before we get to the stories, because deep learning is a specific thing. And if you're going to understand what AlexNet did and why it mattered, you need to understand what is actually running underneath. Deep learning, as Park and Leck define it, is an evolution of machine learning. It uses a programmable neural network that enables machines to make accurate decisions without help from humans. The key mechanism is the artificial neural network, the ANN. Not a metaphor, an actual computational structure loosely inspired by how biological neurons connect and fire. Here's how it works. At the bottom, an input layer. Raw data comes in. For an image, that is pixel values. For text, numerical representations of words. For a medical scan, signal intensities. Whatever the data, the input layer receives it. Above that, hidden layers. Multiple layers of mathematical nodes, neurodes, each receiving weighted inputs from the layer below, applying a function, and passing outputs up. The weights on those connections are what training adjusts. They start random. Across millions of examples, they get refined until the network consistently produces accurate outputs. At the top, the output layer. The answer: cat or not cat, malignant or benign. Which word comes next? The deep in deep learning is the depth, the number of hidden layers. Early neural networks had one or two. Modern architectures have hundreds. That depth is what allows the network to learn increasingly complex and abstract representations. Here is the distinction that matters for everything that follows. Traditional machine learning works in two separate stages. A data scientist manually extracts features from the input, identifies the relevant edges, shapes, and patterns, and feeds those to the model. The model then classifies. Two distinct steps, both requiring human judgment about what to look for. Deep learning collapses that into one. The network learns to extract features and classify simultaneously. You give it raw pixels, it figures out what matters without being told. That is not an incremental improvement. It is a qualitative change in what the technology can do, which also means something uncomfortable. We often cannot fully explain why a deep learning model produces the output it does. IBM Technologies' Jeff Kroom says this directly. With so many layers to the neural network, it becomes hard to decompose and understand exactly what is happening inside. The decisions can be accurate. The reasoning is opaque. Regulators call this the explainability problem. For organizations deploying AI in high-stakes decisions, credit scoring, hiring, medical diagnosis, opacity is not a minor inconvenience. For now, AlexNet, 2012. This is what that architecture could do. 2018. A researcher at MIT named Joy Buolamwini audited facial recognition systems from Microsoft, IBM, and Amazon. Her paper, Gender Shades, found error rates of up to 35% for dark-skinned women. For light-skinned men, under 1%. The same architecture, the discrepancy was in the training data. Underrepresented groups produced less accurate results. The algorithm didn't discriminate intentionally. It reflected the world it had been trained on. And then there was 2020. Protein folding had been an open problem in biology for 50 years. Proteins are molecules that do most of the work in living cells, but their function depends on their three-dimensional shape. Predicting that shape from the amino acid sequence alone had defeated researchers for half a century. In November 2020, DeepMind's AlphaFold 2 entered the biannual Protein Structure Prediction Competition. It solved the problem. not approximately, precisely, at near atomic accuracy for virtually every known protein. Scientists called it the most significant scientific result in decades. DeepMind subsequently released over 200 million protein structures freely to the global scientific community. People sometimes say that AI can't find anything new, that it can only recombine what it was trained on. AlphaFold had been trained on known protein sequences and known structures. The 3D folding patterns it predicted were things no human had found. Biologists have since used those predictions to advance drug discovery for diseases that were previously out of reach. Finding patterns in existing data at a scale and speed no human can match, and those patterns constituting genuinely new knowledge. That is what deep learning made possible. What links AlexNet, Joshua Brown, Joy Buolamwini, and AlphaFold is the same underlying architecture. Layers of neural networks trained on data learning to find patterns. The architecture is neutral. The application, the training data, the governance around deployment, those are where the human decisions live. And by 2022, a different architecture was taking over, one that had already transformed language. We will get to that. But first, the question of what happens when machines try to understand what we say. In 1966, a computer scientist at MIT named Joseph Weizenbaum built a program called ELIZA. It was designed to simulate a Rogerian therapist. It understood nothing. It matched patterns in your text and reflected questions back. I feel lonely. Why do you feel lonely? That was it. Weizenbaum was not proud of what happened next. His own secretary, who had watched him build ELIZA, who understood exactly how it worked, asked him to leave the room so she could have a private conversation with it. He spent the next decade writing about the danger of mistaking machine response for machine understanding. His book, Computer Power and Human Reason, published in 1976, is still cited. The problem he identified in 1966 is still the central problem with large language models today. Does the machine understand, or is it responding? That question drove 60 years of natural language processing research. NLP, the attempt to give machines the ability to understand and generate human language. Progress was slow. The systems were brittle. They worked within narrow domains and broke the moment language exceeded what they'd been trained on. Then, in September 2016, Google made a change that most of its users never noticed. Google Translate had used statistical phrase matching for 10 years. One day, they switched it to a neural network system, GNMT, Google Neural Machine Translation. The improvement was so dramatic that Google engineers thought the deployment had broken something. On language pairs the system had never been specifically trained on, it still produced coherent translation. The model had learned something about the structure of language itself, not just word-to-word mappings. The field moved entirely to neural approaches within 18 months. The same month, March 2016, Microsoft launched a chatbot called Tay on Twitter, designed to learn from conversation. You have already heard what happened. 16 hours. The contrast between GNMT and Tay tells you everything about what the technology could do and what the governance around it needed to be. Before we answer that, the definitions. Because NLP, Transformer, and LLM get used interchangeably in the press, they are not the same thing. Natural language processing is the field. As the University of Arizona defines it, NLP is a branch of AI and machine learning that incorporates the fields of linguistics and computer and data science to enable machines to interpret and derive meaning from human languages, either written or spoken. It is the attempt to bridge the gap between how humans communicate and how machines process information. A transformer is an architecture, a specific type of neural network. AWS defines it this way. A transformer transforms or changes an input sequence into an output sequence. by learning context and tracking relationships between sequence components. Not one word at a time, all words simultaneously. Every element of the sequence evaluated against every other element. That attention mechanism is what gives the architecture its power. In practice, text comes in, a tokenizer breaks it into units, each token becomes an embedding, a numerical vector representing meaning in mathematical space. Those embeddings flow through stacked transformer blocks, each containing self-attention and a feed-forward neural network. Output vectors flow to a language model head, which predicts the most probable next word. That process repeats. The Shawshank goes in, redemption comes out, and a large language model, as the University of Arizona defines it, can process and produce natural language text. It learns from a massive amount of text data, such as books, articles, and web pages, to discover patterns and rules of language from them. GPT-3 had 175 billion parameters trained on 570 gigabytes of text. The word large is not hyperbole. In 2017, 8 engineers at Google Brain published a paper called "Attention is All You Need." The title was a deliberate provocation. The entire field was using recurrent neural networks that processed language sequentially, left to right, one word at a time. The paper argued you could replace all of that with a single mechanism: attention, the ability to weigh every word's relationship to every other word in a sentence simultaneously, not sequentially, all at once. Every large language model today is built on this architecture. It is the most cited AI paper of the decade. GPT-3, released by OpenAI in 2020, was trained on 570 gigabytes of text, roughly the size of a substantial chunk of the internet, with 175 billion parameters. It could write, translate, summarize, answer questions, and generate code without being trained for any specific task. Generality from a single model. That had not existed before. And then ChatGPT in November 2022 put it in front of 100 million people within 2 months. Here is the problem. Large language models predict plausible text. That is what they do. They do not retrieve facts. They do not check sources. They generate the next most likely word given everything that came before. When the output is correct, and it often is, it is because they plausible and accurate overlap. When they diverge, the model does not know. In 2023, a lawyer in New York submitted court briefs citing 6 case precedents. None of them existed. He had used ChatGPT to research the citations. ChatGPT had generated plausible-sounding case names, dates, and rulings. The lawyer faced sanctions. The judge asked for the full citations. There was nothing to show. Mata versus Avianca became the canonical example of what the field calls hallucination. Not a glitch, not a bug, a structural property of the architecture. The model generates what is plausible. Plausible and true are not the same. Fluency is not accuracy. A confident tone is not a verified fact. This is the ELIZA problem at scale. We attribute understanding to a system that is doing something different and, in the right conditions, something extraordinarily useful. But the skill required to use it well is the skill of knowing when to trust it and when to check. In 2026, the frontier has moved again. Reasoning models run internal chain-of-thought processes before responding. They think before they answer. Slower, more compute-intensive, significantly more accurate on complex problems. And RAG, Retrieval Augmented Generation, connects models to verified knowledge bases rather than relying on training memory. The model retrieves, then generates, a meaningful reduction in hallucination for enterprise deployment. Language is where most of us encounter AI. It is also where the gap between what it sounds like and what it knows is widest, which is what made the next development so significant. Because once you could generate language, the question became, can you generate everything else? In August 2022, a man named Jason Allen entered a digital art competition at the Colorado State Fair. His entry was a richly detailed cinematic image, Baroque architecture, soft light, figures in elaborate costume. He titled it Théâtre d'Opéra Spatial. He attributed it to Jason Allen via Midjourney. He won first place. Artists were furious. The debate ran for weeks. The question that the art world couldn't resolve was not really about the image. It was about the three questions that every new capability eventually forces. Who made it? Who owns it? And who is responsible when something goes wrong? Those questions are still open. But the technology that created that image, and the ones that followed, represents the most significant shift in what AI can do. Until 2014, AI could classify. It could predict. It could recommend. It could not create. In 2014, Ian Goodfellow had an idea at a bar after a colleague's going-away party. He went home, coded it overnight. It worked on the first run. He called it a generative adversarial network, a GAN. Two neural networks in competition. One generates fake images, the other tries to detect them. They train each other. As the detector improves, the generator improves. The output of that competition, given enough time and data, is images indistinguishable from photographs, audio indistinguishable from real speech, video of people saying things they never said. Every AI-generated image, deepfake, and synthetic voice traces back to that idea, developed on one night in Montreal in 2014. The course reading, Story and Colleagues, published in 2025, identifies three properties that distinguish generative AI from everything that came before. Strong emergence. Capabilities the model wasn't explicitly trained for, behaviors that appear at scale that weren't in the design. Generative novelty. Output that is genuinely new, not retrieved or recombined from stored data, but synthesized. And systemic input-output. The ability to work across modalities simultaneously, text, image, audio, code, as a unified system. These three properties are why generative AI represents a qualitative shift, not just faster pattern matching, something different in kind. In August 2022, a man named Jason Allen entered a digital art competition at the Colorado State Fair. His entry was a richly detailed cinematic image, Baroque architecture, soft light, figures in elaborate costume. He titled it Théâtre d'Opéra Spatial. He attributed it to Jason Allen via Midjourney. He won first place. Artists were furious. The debate ran for weeks. The question that the art world couldn't resolve was not really about the image. It was about the three questions that every new capability eventually forces. Who made it? Who owns it? And who is responsible when something goes wrong? Those questions are still open. But the technology that created that image represents the most significant shift in what AI can do. Until 2014, AI could classify. It could predict. It could recommend. It could not create. In 2014, Ian Goodfellow had an idea at a bar after a colleague's going-away party. He went home, coded it overnight. It worked on the first run. He called it a generative adversarial network, a GAN. Two neural networks in competition. One generates fake images, the other tries to detect them. They train each other. As the detector improves, the generator improves. The output of that competition, given enough time and data, is images indistinguishable from photographs, audio indistinguishable from real speech, video of people saying things they never said. Every AI-generated image, deepfake, and synthetic voice traces back to that idea, developed on one night in Montreal in 2014. Before we see what followed, one structural point to anchor everything. Generative AI does not sit neatly inside any one box on the diagram. It sits at an intersection. The professor's diagram makes this explicit. Generative AI lives where deep learning and natural language processing overlap. Deep learning provides the computational architecture, the neural networks that learn to generate from training data. NLP provides the language capability, the ability to work with text, meaning, and sequence. When you combine both, you get a system with generative capability across modalities. Large language models are generative AI that works primarily through language. But Gen AI is broader than text. OpenAI's DALL-E generates images from textual descriptions. Codex translates natural language into executable code. These are all generative AI systems, each applying the same underlying capability across a different modality. Jeff Kroom at IBM Technology calls these foundation models. Large systems pre-trained on enormous datasets, general enough to be adapted for a wide range of downstream tasks. The foundation model is not the application. It is what the application is built on. IBM also notes the objection you will hear. Gen AI isn't really creative, it's just recombining what it was trained on. Their answer is a music analogy. Every note has already been invented. Every song is technically a recombination of existing notes in a different order. We still say new music exists, new compositions are real. Gen AI is similar. What gets generated is genuinely new, even if the building blocks are not. Story and colleagues formalize this in the 2025 paper as generative novelty, one of three properties that distinguish Gen AI from everything before it. The course reading, Story and colleagues, published in 2025, identifies three properties that distinguish generative AI from everything that came before. Strong emergence, capabilities the model wasn't explicitly trained for, behaviors that appear at scale that weren't in the design. Generative novelty, output that is genuinely new, not retrieved or recombined from stored data, but synthesized. And systemic input-output, the ability to work across modalities simultaneously, text, image, audio, code, as a unified system. These three properties are why generative AI represents a qualitative shift, not just faster pattern matching, something different in kind. In 2019, a biotech company called In Silico Medicine used generative AI to design a novel drug molecule targeting fibrosis. Normal drug discovery takes 12 years and over $1 billion, from target identification to clinical trial. In Silico went from target to clinical drug candidate in 18 months. The molecule entered phase 1 clinical trials in 2021, the first AI-designed molecule to go into a human body. And then, in 2022, Stability AI released Stable Diffusion as open source, free, runnable on a consumer laptop. Midjourney launched. Anyone with a prompt and a few seconds could generate a photorealistic image of anything. Jason Allen won his competition that August. 2023 arrived, and the consequences came with it. Getty Images sued Stability AI for scraping 12 million copyrighted photographs to train their model, without permission, without compensation. The lawsuit is still active. The legal question, whether training on copyrighted material constitutes infringement, is unresolved globally and will define the industry when it is. SAG-AFTRA and the Writers Guild of America went on strike simultaneously for the first time in 63 years. AI was at the center of both, Studios wanted to scan actors' likenesses permanently. Writers were concerned about AI-generated scripts. Over 100 days of industrial action. The economic relationship between human creative labor and generative AI is still being negotiated. A UK energy company's CEO wired €220,000 to a fraudster who called him using an AI-generated clone of his supervisor's voice. A few seconds of public audio was enough. The FBI issued warnings in 2023 about voice cloning being used in virtual kidnapping scams. The same technology. The drug molecule, the art competition, the voice fraud? The same underlying capability, learning to generate plausible output, applied in every direction simultaneously. Generative AI does not have a ground truth it is working toward. It has a coherence engine. The output can be technically stunning and factually wrong at the same time. The creative output can be genuinely new and legally contested at the same time. The voice can be perfect and fraudulent at the same time. In 2026, the technology is moving toward agentic AI. Systems that don't just generate content, but take actions, plan, decide, execute. The language model becomes the reasoning layer. The question of who is responsible for what it does is more urgent than ever. Which is where we land. The human question. In May 2023, Geoffrey Hinton resigned from Google. He was 75 years old. He had spent his career building the mathematical foundations of modern deep learning. He won the 2018 Turing Award, the Nobel Prize of Computing, alongside Yoshua Bengio and Yann LeCun, for work that made everything in this course possible. He resigned so he could speak freely. He told the New York Times he was scared. Not of AI as it exists today, of the trajectory, of systems developing emergent goals, goals we didn't design, goals we didn't anticipate, and pursuing them more effectively than we could stop. He said he partly regretted his life's work. It is worth sitting with that for a moment. The person most responsible for the technology that AlphaGo, GPT-4, AlphaFold, and every image generator runs on, stepping back from it to issue a warning. Not because he thinks the technology is wrong, because he thinks the question of what we do with it and how we build what comes next is the most important question of our time. Governments have started to answer. The European Union passed the world's first comprehensive AI regulation in March 2024. The EU AI Act takes a risk-based approach. At the base, the widest category, minimal risk, spam filters, games, recommendation systems, no specific regulation. At the next level, transparency requirements. Chatbots must disclose they are AI. AI-generated content must be labeled. Above that, high risk. AI used in hiring, credit scoring, healthcare, education, policing, border control. Mandatory human oversight, third-party audit, and transparency before deployment. And at the top, unacceptable risk, banned. Social scoring systems, real-time biometric surveillance in public spaces, subliminal manipulation of behavior. Any company deploying AI in or to EU markets is within scope. The rest of the world is watching. But regulation is the last line of defense. The first line is leadership. The organizations that get AI wrong are not, in most cases, making technology mistakes. They are making strategic mistakes that precede the technology. They implement AI because everyone else is, because they feel the pressure, because FOMO is real. And it is real. There is genuine cost to falling behind. But FOMO is not a strategy. Start with why. Simon Sinek's framework applies here directly. What problem are we solving? What is the cost of not solving it? What changes for our customers, our people, our operations if we get this right? The reason to implement AI is not AI itself. It is the valuable problems it can solve. Leadership has to own this personally. You cannot delegate the why and what to a technology team. You cannot govern what you don't understand. This is Ethan Mollick's consistent finding from studying enterprise AI adoption at Wharton. Leaders who do not use these tools themselves cannot make good decisions about where and how to deploy them. Think of it like an advanced class. Prerequisites exist, things you need to know before you can take the course. For organizations, those prerequisites are leadership that understands and engages with AI directly, the capability to evaluate output quality, and the process maturity to build governance around what gets deployed. A low-skilled organization will have a poor AI implementation for the same reason it would have a poor ERP implementation or a poor change program. The technology is not the variable. The harms we have documented in this course were not produced by malicious systems. They were produced by well-intentioned deployments that lacked governance. Amazon's AI hiring tool was trained on their own data, the best data available. The data reflected 10 years of biased decisions. The AI learned those decisions and scaled them. The result was discriminatory output that looked like objective process. The Compass recidivism algorithm was used by U.S. courts to predict likelihood of reoffending, informing bail, sentencing, and parole decisions. ProPublica's investigation in 2016 found Black defendants were incorrectly flagged as high risk at nearly twice the rate of white defendants. The algorithm didn't use race directly. It used proxies, zip code, employment history, that were themselves correlated with race through structural inequality. The system encoded injustice and gave it the authority of a number. AI does not neutralize human bias. It encodes it, scales it, and presents it as mathematics. Which is why the augmentation frame, proposed by Paul Daugherty and H. James Wilson in their 2018 book, Human plus Machine, is more useful than the replacement frame. The question is not, what will AI replace? The question is, what can humans and AI do together that neither can do alone? In 1997, after Deep Blue defeated Kasparov proposed a format he called advanced chess, human and AI teams playing together. Human and AI consistently outperformed the best AI alone. The human provided strategic intuition. The AI provided calculation depth. The combination exceeded both. That is the model, not AI instead of humans, AI alongside humans, each doing what they do better. There is a second governance cost that rarely makes the front page: the environmental cost of training. Emma Struble and colleagues calculated in 2019 that training a single large transformer model produces as much carbon dioxide as 5 cars over their lifetimes. In 2026, the models being trained are orders of magnitude larger than those Struble measured. The compute required to run AI at scale consumes electricity at the level of small nations. Microsoft's sustainability commitments, in place before they invested $13 billion in OpenAI, moved in the wrong direction after that investment. The resource cost is real. For organizations making AI investment decisions, it belongs in the ledger. But the human side of that equation requires something that cannot be automated. You have to know what good looks like. You have to be able to evaluate the output, catch what's wrong, and stand behind the result. The AI generates the draft. You are responsible for what leaves your desk. Think of AI governance like CI/CD in software development. Continuous integration, continuous deployment. The principle that no code goes to production without passing defined tests. Structured quality gates. Human review at checkpoints. The more automated the system, the more structure is required, not less. No assumptions. That principle applies to every AI workflow. The more you automate, the more rigorously you need to define what success looks like, how you verify it, and who is accountable when it goes wrong. In 2026, AGI does not exist. The best researchers in the field disagree about when, or whether it will. Jan LeCun at Meta believes current architectures cannot get there. Jeffrey Hinton believes we are closer than most people admit. Sam Altman thinks it may arrive within years. These are the people who built the technology. The uncertainty is real. What is not uncertain is this: the systems we have now are consequential enough to require serious governance, serious ethics, and serious human judgment. We started this course with a smart speaker and a wall. We end it with a question about what kind of future we are building and who is responsible for it. The answer, in every case, is us.